Hello, my name is Kumar Sarv and I am a final year PhD student at TI from Mumbai. Today I will be discussing a general scheduling problem for minimizing age of information, which is a joint work with Professor Rahul Bajaj. To begin with, consider a sensor, which is basically an information source, and a controller that needs the information. At the sensor, information updates are generated intermittently, say at time G1, G2, G3, and so on. And due to system limit, the sensor transmits a subset of these updates to the controller. Let's say this update 1 is generated at G1, the sensor begins to transmit it at time S1, and depending on the transmission delay, it is received at the controller at time R1. Then update 2 is generated at time G2, the sensor does not transmit it. Update 3 is generated at time G3, the sensor begins to transmit it at time S3, and it is received at the controller at time R3, and so on. At any time t, look at the latest received update, look at its generation time. The difference between the current time and the generation time of the latest received update is called the age of information at time t. As we can see, this age of information increases linearly with time, except at time instance when a new update is received at the controller. At this time instant, this age of information decreases to the value which depends on the generation time of the received update. And then again, the age of information increases until the next instant when a new update is received, and so on. So as we can see, this age of information is basically a metric which quantifies how old information at the controller is at any time. Now, for obvious reasons, the information available at the controller is required to be, should not be old, and which means that the age of information should be small. But age of information minimization requires frequent transmission, because as we saw, this age of information increases linearly with time unless a new update is transmitted. So basically, so age of information minimization requires frequent transmission, and transmission consumes energy. So there is a trade-off between age of information and energy. This trade-off is analyzed by considering transmission cost. So whenever an update is transmitted by the sensor, it incurs a cost of C units. So the problem is to minimize this average age of information and average transmission cost, and the decision to make at each time is to which update to transmit. Now, in practice, we may not have a single sensor, but in fact multiple sensors which may be trying to transmit its update to the controller. In this work, we consider this setup with multiple sensors. We assume that at each sensor, updates are generated intermittently with intergeneration time uh, according to some general distribution. For sensor L, the intergeneration time is IID, independent and identically distributed according to some distribution GL. Also, the time required for sensor L to completely transmit its update, completely transmit one update is DL, which is again random as per some general distribution DL. Also, at any time, at most one of the sensors can transmit, which is decided by a centralized scheduler. Also, the sensor that transmits incurs transmission cost, which is CL for sensor L. In this work, we restrict ourselves to non-preemptive setting, that is, any ongoing transmission cannot be preempted. So once a sensor begins to transmit, the scheduler can choose another sensor to transmit only when the ongoing transmission completes. And the objective is to minimize the weighted sum of the average age of information and transmission cost of all sensors, which is formally given as follows, where this WL denotes the weightage of sensor L, this AOIL is the average age of information of sensor L, CL denotes the cost per transmission for sensor L, and RL denotes the number of updates sensor L transmits per unit time. And the decision to make at each time is which sensor gets to transmit and which update the sensor should transmit. And the decisions have to be made based only on causal information. Now note that at times scheduler may not schedule any sensor for transmission. This may be due to any reason. such as due to transmission cost. So although we are considering setup with multiple sensors, even with a single sensor, optimal policy is known for few special cases only. So the causal scheduling policies are analyzed using competitive ratio metric, which is by comparing against the performance of an offline optimal policy. The competitive ratio of a causal scheduling policy is equals to the expected cost for the policy divided by the expected cost for an optimal offline policy. With respect to this work, the most relevant prior work is by Cadota and Modiano, which appeared in 2019. It considered discrete time setting and only restricted itself to only geometric distribution and zero transmission cost, and derived causal policies with competitive ratio at most 4. In this work, we consider continuous time setting and general distribution GLs and DLs for update intergeneration time and transmission delay. Also, there may be non-negative cost for transmission. For this problem, we propose a randomized scheduling policy and derive an upper bound on its competitive ratio, which is independent of transmission delay distributions. Also, for several common update intergeneration time distributions, such as exponential, uniform, and Rayleigh, this competitive ratio is upper bounded by 4. And now coming to the policy, the proposed randomized policy has two parts. Part 1 is for update selection, it chooses which update to transmit when a sensor gets to transmit, and the second is the sensor selection, which chooses which sensor gets to transmit at any time. First, update selection. So at each sensor L, whenever an update is generated, the update is marked with a fixed probability PL, independent of everything else, where this PL is found by minimizing an upper bound on the cost for the policy. Updates that are not marked are discarded. This happens with probability 1 minus PL. So whenever an update is generated, it is either discarded, which happens with probability 1 minus PL, or the packet is marked with probability PL. Now, at any time, when sensor L is selected to transmit, it immediately transmits its latest marked update. Now, sensor scheduling, for each sensor L, we define probability QL, which is inversely proportional to the mean intergeneration time of marked updates at sensor L, which is proportional to this PL over the PL, which is the update marking probability, divided by the mean of the update intergeneration time of updates at sensor L. And we normalize these QLs such that their sum is equals to 1. Now, among all sensors at any time, schedule sensor L probability QL. The intuition for the policy is as follows. So this update selection, it makes an update eligible for transmission with probability PL, and this probability PL depends on all other sensors and is obtained by minimizing an upper bound on the transmission cost. So this update selection is critical for managing transmission cost, as it restricts the subset of updates that may be transmitted. Further, this sensor scheduling, it controls the frequency at which a sensor transmits its marked update. As we said, the update marking probability is obtained by minimizing an upper bound on the cost. So let's look at the upper bound. So at each sensor L, updates are marked by the randomized policy. Let TIs denote intergeneration time of marked updates at sensor L. For this randomized policy, these TIs are independent and identically distributed. Further, let S1, S2, S3, and so on denote successive time instants when sensor L is selected to transmit. Let ZIs denote delay between the successive times when a sensor is selected. For this randomized policy, these ZIs are also independent and identically distributed. Now note that because the sensor gets to transmit every ZL time units, ZL is random. The the difference between when an update is the generation time of a marked update and when it is when the sensor begins to transmit it is at most Z. Now, this in intergeneration time of marked updates. Note that it depends only on the update generation process and the update marking probability, and this Z. That is time between difference between successive time instants when a sensor gets to transmit depends on the transmission delay processes and the sensor selection. Now these update generation process and transmission delay process are independent of scheduling policy, and also they are independent of each other. In contrast, these update marking and sensor selection, these are related. The parameters for these parameters PL for update marking and QL for sensor selection, these are related such that the expectation of this product of TZ is less than equals to square of expectation of T. This is because the update marking and this sensor selection, both the processes are independent for this randomized policy, but the parameters PL and QL are related. So expectation of TZ is equals to the product of expectation of T and expectation of Z, and this expectation of Z is upper bounded by expectation of T, so we get this relation. Now using this relation, we can basically upper bound the the contribution of the delay in the delay in the total cost for the randomized policy with respect to the cost because of intergeneration time of marked updates, and we can get an upper bound which is independent of the transmission delay distribution. Further, this expectation of TL, so this upper bound only depends on expectation of TL and the other constant parameters. Now this expectation of TL, this is equals to the mean intergeneration time of updates at sensor L divided by the update marking probability PL. Now substituting it into the derived upper bound, we get an upper bound on the expected cost for the randomized policy, which is in terms of PL, and rest are all constant. So this is, we see that this is this upper bound is a convex function of PLs. So being a convex function, it is easier to minimize. So we find the parameter, the values of PLs that minimize this upper bound, and we use that value of PL in the algorithm. So we have this main result. That is, we have a competitive ratio upper bound for the randomized policy, which is independent of transmission delay distributions, and is at most 4 for common update intergeneration time distributions. Also, we show that the analysis for this considered policy is tight. That is, the dependence of the competitive ratio on the update intergeneration time distributions is unavoidable for this policy. We show this by deriving a lower bound on the competitive ratio. We do this by constructing an example where we show that for the example setup, the cost incurred by the randomized policy is a certain factor times the cost incurred by an optimal offline policy, and that factor is basically proportional to the ratio of the variance and mean square of the update intergeneration time distribution. So basically the setup is as follows. So we consider a single sensor where updates are generated intermittently. The intergeneration time of updates are either epsilon, where epsilon is a small positive constant. So this intergeneration time is either epsilon with probability half, or it is A. It is a constant A with probability half, where this A is a large constant. So either the update intergeneration time is A, it is epsilon, so on. Also, we consider zero transmission delay and zero transmission cost. So for this setup, optimal policy is obvious. So because there is no transmission cost and no transmission delay, transmit all updates immediately after generation. For this optimal policy, the cost is upper bounded by the mean update intergeneration time uh, for sensor L. Further, for this setting, we compute the lower bound on the expected total cost for the randomized policy. We find that the lower bound depends on the variance and mean of update intergeneration time distributions for sensor L. Using the two derived bounds, we get a lower bound on the competitive ratio of the randomized policy, which is proportional to the ratio of the variance and the mean square of the update intergeneration time distribution of the sensor. So in summary, we consider a general setting with multiple sensors, um, arbitrary update intergeneration time and transmission delay distributions, and non-negative transmission cost. And we proposed a novel two-stage randomized policy and derived an upper bound on its competitive ratio, which is independent of transmission delay distributions, and is at most 4 for common update intergeneration time distributions, such as exponential, uniform, and Rayleigh. Thank you.